This is Donna Nelson at the University of Oklahoma. So now we are going to look at the fifth and final lecture of carboxylic acids and their derivatives. And so this is going to be the reactions of amides and also nitriles. And so let's go ahead and look at this, the preparation and reactions of amides, and then we'll look at nitriles and a little bit about synthesis strategies. So amides can be created from any of the other carboxylic acid derivatives because they are the least reactive. All of these are most reactive. It's easy to go energetically downhill. However, it is implied here, but not actually stated. I will tell you that you can't go uphill energetically. You can't create an acid chloride directly from an amide. So if you want to go uphill here, you have to hydrolyze this to the carboxylic acid, and then from the carboxylic acid, go to the acid chloride. Or you can hydrolyze this to the carboxylic acid, and from the carboxylic acid, go to the anhydride. If you want to go uphill, you have to go through the carboxylic acid. But amides can be generated from any of these. The most popular way is using two equivalents of ammonia to simply react with the carboxylic acid chloride. And remember, you're going to be generating HCl. When your NH3 goes in and reacts here, you're going to wind up with NH2, so you're going to have HCl. And the second equivalent of the ammonia will be used just to pick up the HCl and neutralize the HCl and be able to remove it from the reaction. Excess LAH will once again convert the carbonyl to the methylene, just as you've seen before. Amides can be hydrolyzed with dilute acid to give you the carboxylic acid. But it's not a great reaction in the heat. It is high temperatures. So let's look, however, at the mechanism for that reaction. It's good for you to see as many of these mechanisms as possible. A pair of electrons on oxygen picks up a proton and leaves you with water. A pair of electrons on oxygen here comes in for attack, and remember the carbonyl is activated because you've protonated it. Then the pair of electrons in the pi bond moves out onto oxygen, and now this oxygen is protonated, and that proton is removed using a molecule of water. So the pair of electrons on oxygen picks up a proton. The pair of electrons in the OH bond moves back onto oxygen, satisfying that positive charge. Then, remember, compare your reactant to the product, and you can look at what you need to remove and what you need to enter. And here you need to remove the nitrogen. So now here you have oxygen, oxygen, nitrogen. So you have to keep your goal in mind. So you're going to protonate the group that you need to remove. So nitrogen is going to pick up a proton. Remember, this is acidic conditions. So throughout here you have water bearing positive charge. This is acidic conditions. And so when the nitrogen picks up a pair of electrons, it bears a positive charge now. This is a neutral leaving group. You've converted this amino group to an ammonium group, which is a neutral leaving group. So you've set this up with, prepared it to lose this molecule. Pair of electrons on oxygen moves back in, forms the pi bond, and that forces the NH3 off because carbon cannot have more than 4 bonds. And so then this oxygen is going to be bearing a proton and a positive charge, and so nitrogen picks up a proton and neutralizes the carboxylic acid so that it is no longer protonated. So this is why you need, so here is your ammonium group that has departed. Amides can be hydrolyzed under basic conditions as well. So notice here you have the base. In step 1, it will be under basic conditions. In the second step, it will be neutralized with a dilute acid. And so this is going to be much shorter. Now you simply have hydroxide come in, do a backside attack on the carbonyl. You don't need to activate the carbonyl because this is a stronger nucleophile. And then the pair of electrons on oxygen moves back in, reforms the pi bond, and NH2 minus departs and very rapidly deprotonates the carboxylic acid that was just formed. And so now you have the carboxylate. On nitriles, preparation of nitriles, when a primary or secondary alkyl halide is treated with cyanide, the cyanide acts as a nucleophile in an SN2 reaction. So here you see that that was covered in chapter 7 of Klein's textbook. So here we have cyanide come in, do a backside attack, displace bromide. So the sodium cyanide still have the same counter ion, so you have sodium bromide now. So here is your nitrile. Nitriles can also be made by dehydration of a primary amide by using different reagents such as thionyl chloride. So this is converted a primary amide, no other substituents on amine, so and a primary alkyl group, and it's been converted to a nitrile. So let's look at this. The pi electrons do an attack at sulfur, which is bearing a positive charge because it is attached to 3 electron withdrawing groups. And the pair of electrons in the sulfur-oxygen pi bond moves out onto oxygen. Then the pair of electrons on oxygen moves back in, reforms the sulfur-oxygen double bond, or pi bond rather, and chloride departs. So now you have this intermediate, which still has the nitrogen bearing a positive charge. Now, you have a base, comes in, deprotonates, removes this proton, and so the pair of electrons in an NH bond moves back onto nitrogen, satisfying the positive charge on nitrogen. Then we go on down here. A base removes a second proton from nitrogen. That pair of electrons moves in, forms the CN triple bond, and this carbon-oxygen bond breaks along with the sulfur chloride bond also breaking, and so that gives you these 3 products. You have the nitrile formed from this, you have SO2 formed from that, and then the chloride comes from this part of the molecule. Nitriles are hydrolyzed to carboxylic acids under acidic conditions. Now, when any of the carboxylic acid derivatives are hydrolyzed, the product will be a carboxylic acid. I don't know if you've noticed that, but you can go back and look at it, and that is true. So here we see the nitrile being treated with dilute acid and heat, and the amide is generated from that. And when that is hydrolyzed farther, one can obtain the carboxylic acid. So here's the mechanism for that. First, the nitrile is protonated on nitrogen. Nitrogen is now bearing a positive charge. Then a pair of electrons on oxygen comes in, does an attack at this carbon atom. A pair of electrons in one of the pi bonds moves out onto nitrogen, satisfying the positive charge on nitrogen. So oxygen is now protonated. A pair of electrons on oxygen picks up a proton, satisfying the positive charge on nitrogen, and so that protonated water then delivers a proton to the nitrogen, generating the imide functionality. So, then we come down here. Now that you have nitrogen bearing 2 protons, nitrogen is bearing 2 protons, using these arrows show the resonance structures. Using this resonance structure, water can remove another proton from the oxygen, satisfying the positive charge on oxygen. And so now you see the formation of the product. Let's go back and look at something. Okay, so we have gotten as far as the amide. And so this shows the basic conditions for hydrolyzing the nitrile to the amide. Pair of electrons attacks at carbon. The pair of electrons in one of the pi bonds moves out onto nitrogen. Nitrogen is bearing a negative charge and abstracts a proton from water. Then the base that is generated deprotonates the hydroxyl group. A pair of electrons, the pair of electrons on oxygen moves in, forms the carbonyl, and a pair of electrons in this pi bond moves out onto nitrogen, forming a negative charge, which then deprotonates water. So the mechanistic steps here are basically the same, except there's not all of this protonation, deprotonation, protonation, deprotonation. So a lot of the protonation, the deprotonation steps are removed. Nitriles can react with Grignards to form a ketone. So the alkyl group, and it doesn't matter whether it's analogous to this alkyl group, they can be the same or different. This alkyl anion attacks carbon. The pair of electrons in one of the pi bonds moves out onto nitrogen, and then this can be hydrolyzed to the pi bond and the carbon-oxygen pi bond. And we've seen this, the mechanistic steps for this previously, so I'm not going to go through that again. Here with LAH, lithium aluminum hydride, the nitrile can be converted to the primary amine. And so this is using LAH followed by water to just neutralize the reaction. So overall, there are 2 kinds of bond-forming reactions in this chapter. There's the one in which the bond-forming reaction, the functional group remains in the same location. So you can see the the functional group is changed. The functional group on the carbonyl or on the carbonyl carbon changes, but the carbonyl carbon itself stays intact. There is elaboration done at the carbonyl carbon. We also have carbon-carbon bond forming reactions in which the cyano group comes in, does a backside attack, or the Grignard is created and then reacts with carbonyl. So here we have increased the carbon skeleton by 1 carbon in both places. So the location of the functional group has changed. So the location of the functional group is going to be on, it starts out on 1 carbon, and at the end of the synthesis, it's actually on another carbon. So here the functional group stays on the same carbon. In these reactions, the functional group moves by 1 carbon. And you can think back onto the reactions in chapter 7 and also, I believe, in chapter 13, where the functional group starts out and then it reacts with an epoxide. So here, this carbon will become attached to carbon 1, and the functional group now winds up on carbon 2. So the functional group, the point at which the carbon skeleton is going to be further elaborated, is moved over by 2 carbons. So here, the elaboration stays on the same carbon throughout. In these, the elaboration is moved over by 1 carbon, and here the functional elaboration is moved by 2 carbons. So that shows you the 3 different types of synthesis strategies, the 3 different types of bond-forming reactions that you've had. This is a good study sheet. You can see all these different reactions of the carbonyl compounds presented on one sheet. You can print this off using from the PowerPoint slide that you see right now. A good way to study would, if you're motivated, if you're really motivated to study, you can go in and white out these reagents and then make a copy of the sheet that you've whited out everything on, or make several copies, and then go in and test yourself and see if you know the reagents that are needed to do each one of these transformations. Or you can go in and white out the reactants in each case and create a study sheet by making a copy of that page that has all the whiteout on it, and then see if you can go in, if you know what the different reactants are supposed to be. So this concludes our chapter 20. This is the last lecture on carboxylic acid derivatives.